So diffusion is just, spontaneous means every single time the gas goes into the air, it's going to diffuse and spread out throughout that container, whatever the container is, or the room, or however you want to say that. But that is diffusion. That's really all we're going to talk about, diffusion. You guys have done diffusion, haven't you, in biology? They call it like osmosis, where you have that bag and you have movement of water molecules either in or out based upon concentrations, right? Well, it's the same idea. It spontaneously does that, right? When you put it in there, it either gets bigger in size or smaller in size because the water spontaneously will equal out. And so gas particles do the same thing, right? Now, effusion is a little bit more specific in that it's kind of like this valve here that I have on the gas jets. If I open that up, that's that movement through a small opening. Okay? And so I've got a symbol for that here on this next slide that we'll take a look at. But effusion is just like a balloon will lose air or lose helium as it sits because there's openings in the... You guys ever see the trick where the guy puts a needle through the balloon and pulls it out and it stays? It doesn't pop. You never seen that?
No. Can we please see a video?
No. You can.
Can we see a video?
I can't do it.
Why can't you do it?
Okay?
Can I look it up?
No. So when it puts it through and it takes it out, it shows that the balloon has tiny openings.
We'll just try it.
Okay? So effusion is a movement of a gas particles through a small opening. Alright? So, kind of show you a little bit about what this entails, kind of a model of this. So, I'll have you copy this down so that, just copy it down real quick, and then we'll explain some different parts of this, what this means. Okay? Just copy that down if you would. Okay. So this is a really pretty easy concept, easy topic. We'll use this equation later. Okay? So common sense, we'll take a look at particles. We have two particles in these. These represents a flask, a sealed container that we have. So we have helium in this container, and we have, this is just methane gas, CH4 is methane. And what we will do, we'll open up this valve, and I've got a question for you, and I think most of you would be able to tell me the answer to this when you see it, or when you guys verbalize it, is if we open up that container, they're going to flow back and forth, right? Because effusion says that you're going to have a movement through a tiny opening. So both gases are going to move both ways. Which one is going to move faster through that opening? Well, we have helium or CH4? I think CH4. Okay? So what tells you that CH4, by looking at this, why do you pick CH4? What's your reasoning?
It has more.
It's got more particles.
Okay, that's just the molar weight of it. So if I have CH4 and I have 16 grams in there, that's 1 mole. In this one, if I have helium, I got 4 grams of that, that's 1 mole. Does that make sense? So both of them have the same number of particles. Do you agree with that? Because they're both...
The particles is way different.
Okay, so let's look at the size of the particles. Which one has the bigger particle, CH4 or helium? Okay, CH4 is bigger. So bigger molecules, are they going to move faster in speed or slower than speed?
Slower.
Slower, okay.
So HE will.
So when we look at how fast they're moving, helium is moving faster than CH4 because it's lighter in weight and smaller. So helium will move faster through this opening than CH4. And that goes with any gas. So if I have two gases I'm comparing, and the lighter one's always going to move faster and move through that opening faster than the heavier one. Does that make sense? Okay. In a lot of ways, that's kind of some analogy, some common sense. You can see, yeah, lighter ones move faster, and since they're moving faster, it's like a race. The faster one's going to win. So the rate's going to be faster. Okay? So what we're going to do is we're actually going to compare their rates to where we know how much faster it moves. So before we do that, I want to look at A and B. And you guys tell me which ones move faster if I compare these two. And we put these two up here. We're not going to. Let's say we do. So what's the formula for bromine gas?
BR2.
BR2. And I'm going to go ahead and figure the molar mass for you. It's 160. Okay, sulfur dioxide, what's its formula?
SO2.
SO2. So SO2 is 1 sulfur is 32, 2 oxygens, 32. That'd be 64. So which one moves faster?
Sulfur dioxide.
Sulfur dioxide. Pretty easy, right? Lighter it is, faster it moves. NH3, 17, HCl, 36.5. Which one moves faster?
NH3.
NH3. Any questions with that? NH3 moves faster, lighter molecule. All right. Now this here is, the first one's going to be easy. The second one, I have to plug in your square root. So let's compare HE and CH4 and see how much faster HE is compared to CH4. What I want to do is, when I do this, I always like to put the smaller molecule up there, or atom, and I always want to take this one and make this the larger molecule. And I'll explain why here in a second. You can do it either way. It makes more sense when you have the smaller one, rate of the smaller one above the larger one in this original setup. Okay? So let's look at this one here. So if that's the case, I want to do it just like helium and CH4. I'm going to put rate of what above. So which one do I want to put above? HE or CH4?
HE.
All right, HE. Then down below, the rate of B would be CH4. Okay, any questions with that? Now, I'm going to set that equal. Right? And I'm going to erase this larger molecule down below because I've ran out of room. I need to put this on the same page. So what I'm going to do is up here, I'm going to take the square root of the molar mass of B. Which one is B? CH4 or HE? CH4, right? Okay, so I'm going to put square root of 16, and what is square root of 16? 4. Then down below, because it's inverse, down here I'm going to put the square root of 4, which is what? 2. So my answer is going to be 4 over 2 or 2 over 1. So how much faster is helium than CH4?
2.
Twice as fast. Twice as many molecules move through this opening here. 2 times. Okay? Versus coming the other way. Does that make sense? Right. Now, what I want you to do is numbers that don't work as well. Why don't you tell me how much faster sulfur dioxide is compared to bromine, so you got another example to look at. Okay? Do bromine versus sulfur dioxide. Okay, do that one. So again, that would be rate of SO2 over rate of Br2. Then you invert them, square root of 160 over square root of 64. And that would get your answer. Does anybody need to do the lab? They were gone. Is everybody here to do the lab yesterday?
I watched those sometimes. Still.